Hello, everyone. So last time we were doing number theory and we looked at Fermat's little theorem. Fermat's little theorem, which was saying that, a to power p minus 1 is congruent 1 mod p if, of course, p does not divide a and if p is a prime number. And we also looked at the concept of primitive root of unity. So a is called a primitive root of unity if a to power p minus 1. So let me say a is a root of unity in Zp if a to power, if p minus 1 is the smallest integer such that a to power p minus 1 is congruent 1 mod p. Now, if a is not 0 in Zp, meaning that if a is not divisible by p, but Fermat's little theorem guarantees that a to power p minus 1 is congruent 1. But the question is a raised to some power smaller than p minus 1 also congruent 1? Or is p minus 1 the smallest power that a to that power will become 1? Now, if p minus 1 is the smallest power, we call that number primitive root of unity in Zp. And otherwise, it's not a primitive root of unity. Okay, the next concept we want to look at is a concept called quadratic residues. Again, let p be a prime number. We say that a is a quadratic residue mod p if a is congruent, let's say, b squared mod p for some b in Zp. So if a, so remember when we work with Zp, our universe is Zp, meaning that every calculation is done mod p. So we won't have any equality anymore. Anything equality here, new equality here is it means congruence mod p. Now, if a is congruent, congruent b squared for some b, then we say a is a quadratic residue. So please note that if this was an equality, let's say, then we would call a perfect square, right? If a is equal to b squared, then we call a is a perfect square. But because here we don't have equality and we have congruence mod p, the term that we use is called quadratic residue. And otherwise, we say that a is a quadratic non-residue mod p. So let's look at an example. Okay, before giving the example, let me also introduce a notation. So definition, again, if p is a prime number, and let's say a is in Zp, we write, So this notation, A over P, but in bracket, equals 1 if A is a quadratic residue and we write A over P equals -1 if A is a quadratic non-residue. So by the way, normally we assume A is not equal to 0 because, I mean, of course, 0 is always 0 squared, but we exclude 0. So let me write in the beginning that we say that A not equal to 0 in ZP. Okay, so A also here not equal to 0 in ZP. And then A over P. So you may wonder, why do we say A over P? Well, A is a number in ZP and P is a prime. For example, A over P could be, if P is, let's say, 5 and A is 3, then A over P could be 3 over 5. Why do we say 3 over 5 equals 1? Well, this is just a notation in number theory. So A over P has nothing to do with the fraction A over P. Of course, A over P is a number between 0 to 1. But here we say A over P. So this is just a notation in number theory. A over P with a bracket. It's just a notation and is defined to be 1 if A is a quadratic residue, and is defined to be -1 if A is a quadratic non-residue. So this notation here, so the notation A over P is called the Legendre symbol. This notation is called the Legendre symbol. So it's not an actual fraction. It's just a notation. Okay. Now let's look at an example. Let's say P equals 5. So which numbers are quadratic residues and which numbers are not quadratic non-residues? So any number of the form B squared, by definition, is called quadratic residue. So let's look at quadratic residues. So we said that we exclude 0, but other than 0, 1 squared is a quadratic residue because it's something of the form is of the form B squared. And 1 squared is, of course, 1. What else do we have? 2 squared. 2 squared is 4. We also have 3 squared. 3 squared is 9. But 9 is same as 4, right? Because we are in Z5. Remember, we said when our universe is Z5, every calculation is done mod 5. So every equality means equality in Z5, which means basically congruence mod 5. So 9 and 4 are equal in Z5, or mod 5 in other words, because 9 minus 4 is divisible by 5. And what is the next number? So then we have 4 squared, which is 16, and 16 is same as 1 in Z5 because 16 minus 1 is 15, which is divisible by 5. And then 5 squared, 5 is again 0 in Z5, right? So, and we said we exclude 0. So quadratic residues, we have 1 and 4 only. 1 and 4 are the only quadratic residues, and other numbers will be automatically quadratic non-residues, which means 2 and 3. quadratic non-residues. So in Z5, we have 2 quadratic residues, 2 quadratic non-residues. So what do you think in ZP would hold? What would be the general rule in ZP? In Z5, we have 2 quadratic residues, 2 quadratic non-residues. In ZP, what is your guess? So theorem. In ZP, we have, so the number of quadratic residues and quadratic non-residues were equal here, right? And same thing happens in ZP. So in ZP first, we said we have to exclude 0. So other than 0, we would have p minus 1 numbers. Now half of these will be quadratic residues and half of these will be quadratic non-residues. So in ZP, we have p minus 1 over 2 quadratic residues and p minus 1 over 2 quadratic non-residues. Okay. Okay, so let's see how we can prove this theorem now. So it's the idea is same as what we did for Z5. So quadratic residues means all numbers of the form b squared. And of course, except 0. So again, let's put 0 aside. And what will be left for us? So proof. So quadratic residues in ZP will be 1 squared, right? 2 squared, 3 squared, all the way to p minus 1 over 2 squared, then p plus 1 over 2 squared, and all the way to p minus 1 squared. Seems that the screen was freezed. Let me see. Yeah. Let me stop share. Okay. So these are quadratic residues in ZP, any number of the form b squared. But right now it seems that we have p minus 1 of them. But as we saw in the example, see, we had the first two numbers were distinct, but then the next 2 numbers were same as the first 2 numbers. So same thing happens here. So we would have 1 squared, 2 squared, 3 squared, all the way to p minus 1 over 2 squared. So these numbers are distinct. I'm going to show that in a few moments. But the first thing I want you to notice is that this number, p plus 1 over 2 squared, is same as p minus 1 over 2 squared, mod p. Why? Because this number can be written as p minus 1 over 2 squared, which is same as p minus 1 over 2 squared. Right? P minus 1 over 2 is same as p plus 1 over 2. And p minus 1 over 2 is same as p minus 1 over 2, because remember p is 0 in ZP. Any multiple of p is 0. So this is same as p minus 1 over 2 squared. So all the way to, so then the next one, so these 2 are equal. Then you will see that the one after this term, is equal to the one before this term. So the one before this term is p minus 3 over 2. The one after this term is p plus 3 over 2. So these two will be, the square of them will be equal. And so on and all the way until the first one will be same as the last one, right? So p minus 1 squared is same as, because p is 0, is same as minus 1 squared, which is same as 1 squared. So at most, I have p minus 1 over 2 squared, because the next p minus 1 over 2 numbers are exactly same as the first p minus 1 over 2 numbers. But still, I haven't shown whether the first p minus 1 over 2 numbers are actually distinct or no, because there is a possibility that, for example, the third number is same as fifth number, or fifth number is same as sixth number, and so on. But if I show that the first p minus 1 over 2 numbers are really distinct numbers, then it means that they're exactly p minus 1 over 2 quadratic residues. So next, we will show that 1 squared and 2 squared all the way to p minus 1 over 2 squared are distinct mod p. So if I squared, let's say, equals j squared in ZP, or mod p, doesn't matter how you write it, you can say they're equal in ZP or congruent or equal mod p. Then that means p divides I squared minus j squared, right? Because then I squared minus j squared will be 0 mod p. And that means which numbers are 0 mod p? Which numbers are 0 in ZP? Multiples of p. So that means p divides I minus j times I plus j. So now if I'm talking about these numbers, the list of these numbers, if I and j come from these numbers, then I plus j will be at most p minus 1, right? Because I and j are between 1 to p minus 1 over 2. So see, that means p divides I minus j, or p divides I plus j. Remember, we had a fact from that we saw before, that if a prime number p divides ab, then p divides a or p divides b. Now, this one is not possible because I and j are both between 1 and p minus 1 over 2. Here, see, I and j are between 1 and p minus 1 over 2. So I plus j will be less than equal to p minus 1, bigger than equal to 2. And none of the numbers between 2 to p minus 1 are divisible by p, right? If p is prime, then 0 is divisible by p, and then the next number divisible by p is p itself, and then 2p, and then 3p. So no number between 2 to p minus 1 is divisible by p. So that means p does not divide I plus j. So I am left with the possibility that p divides I minus j. And that means I minus j equals 0 mod p, right? Remember, multiples of p are 0 in ZP or mod p. And that means I equals j mod p. So if square of two numbers are equal, then the two numbers must be equal themselves, right? So that means 1 squared, 2 squared, 2p minus 1 squared are distinct. So 1 squared and 2 squared are distinct because 1 and 2 are different, right? And then 2 squared and 3 squared are distinct because 2 and 3 are distinct, and 1 squared and 3 squared are also distinct because 1 and 3 are different, and so on. So here I have list of p minus 1 distinct p minus 1 over 2 distinct numbers. And according to what I showed here, which said if square of two numbers are equal, with I and j between 1 to p minus 1 over 2, then the two numbers themselves must be equal. So we showed if I squared equals j squared and I and j between 1 and p minus 1 over 2, then I must be equal to j. Thus, 1 squared, 2 squared, up to p minus 1 over 2 squared are p minus 1 over 2 distinct numbers in ZP. So I'll repeat the reasoning one more time. So if square of two numbers are equal, then the numbers must be equal, as long as the numbers are between 1 to p minus 1 over 2. And here I have list of numbers that are all between 1 and p minus 1 over 2. And because the numbers are distinct, any two of them are distinct, therefore the square of them must be, square of any two of them must be also distinct. So here I have the list of p minus 1 over 2 distinct numbers in ZP, which is the list of all quadratic residues in ZP. Why? Because remember that the next p minus 1 over 2 numbers, as we said, are same as the list of next p minus 1 over 2 numbers in ZP is same as the list of first p minus 1 over 2 quadratic residues. So, and these are all distinct, and these are all same as these ones. So in total, I have p minus 1 over 2 distinct quadratic residues in ZP. In total, we have p minus 1 over 2 quadratic residues in ZP. And therefore we have, the rest will be automatically quadratic non-residues. So we have p minus 1 over 2 quadratic non-residues in ZP. Okay. Now the next theorem we want to show is that if p is prime, then the Legendre symbol a over p is equal to a to power p minus 1 over 2 in ZP. A over p, the Legendre symbol, if you remember, we said it's just a symbol, it's just a notation in number theory. How is it defined? It's defined to be 1 if a is a quadratic residue, and if it's defined to be minus 1 if a is a quadratic non-residue. So, and we are saying that this is equal to a to power p minus 1 over 2. But can we say the same thing about a to power p minus 1 over 2? Can we say that a to power p minus 1 over 2 is also either 1 or minus 1? Well, the answer is yes. A to power p minus 1 over 2 mod p is also always either 1 or minus 1. Please remember that according to Fermat's little theorem, a to power p minus 1 is 1, right? Remember Fermat's little theorem? I also recalled you today. So if a to power p minus 1 is 1, a to power p minus 1 over 2 should be either 1 or minus 1, right? See, if square of a number is 1, then the number itself is 1 or minus 1. This is true in the set of integers. It's also true in ZP as well.
Because you may tell me, okay, we know that in the set of integers, if square number is 1, then the number is 1 or minus 1. But we said that here our universe is ZP, and every calculation is done mod P. Can we still say that in that universe, that in ZP, if a square of a number is 1, then the number is 1 or minus 1? The answer is yes. Still in the universe of ZP, we can still say this fact. I think we proved this last time with 2 different solutions. If you look at the last time lecture notes, you'll see about this fact. Okay, so the right side is also either 1 or minus 1. Left side also always 1 or minus 1. And these 2 numbers we are claiming that are always equal to each other. So this is called the Euler criterion. So this theorem is called Euler criterion. So first, let's look at an example, and then we'll see the proof. So for example, we saw that if P equals 5, then for example, 4 is a quadratic residue. That means 4 over 5, the Legendre symbol is 1. So what about the other side? 4 to power 5 minus 1 over 2 means 4 to power 2, which is 16, which is equal to 1 in Z5. 16 and 5 are equal in Z5. And 4 over 5, the Legendre symbol is also 1. So that means 4 over 5 is equal to 4 to power 5 minus 1 over 2. So this is just an example of this theorem. This theorem says that for every prime number P and for every A, which is of course not 0, then for A not equal to 0 in ZP, so this is just an example of this theorem. P5 and A is 4 here. And we saw that 4 over 5 is same as 4 to power 5 minus 1 over 2. But of course, if you want to prove the theorem, you have to provide a proof that is valid in general, not just with examples. So let's see how we can prove the theorem. So proof of theorem. Okay, what do we know? We know that A to power P minus 1 equals 1 in ZP by Fermat's little theorem. Fermat's little theorem said that A to power P minus 1 is 1. Now, what does that mean? So that means P divides A to power P minus 1 minus 1, right? If A to power P minus 1 equals 1, that means A to power P minus 1 equals 0 in ZP. And if a number equals 0 in ZP, means that number is divisible by P. So A to power P minus 1 divisible by P, then I want to write this one as A to power P minus 1 over 2 minus 1 times A to power P minus 1 over 2 plus 1. See? X minus y times x plus y is equal to x squared minus y squared, right? So now if you look at this one, x minus y times x plus y, the answer will be x squared minus y squared. Now A to power P minus 1 over 2 squared, according to according to the properties of exponents, is A to power P minus 1. And 1 squared is of course 1. So this expression is same as this expression. Now, what does that mean? So that means P divides A to power P minus 1 over 2 minus 1, or P divides a to power p minus 1 over 2 plus 1. Okay, now if A is a quadratic residue, what can I say? So if A is a quadratic residue, no, if A is a quadratic residue, then A will be equal to some B squared, right? A will be equal to some B squared. And what can I say about A to power P minus 1 over 2? Therefore, for some B in ZP, of course, that one also not equal to 0. If A is not equal to 0, B will be also not equal to 0. Because if B is 0, A will be 0. And thus, A to power P minus 1 over 2 will be how much? Will be B squared to power P minus 1 over 2. And that's same as B to power P minus 1, which is equal to 1, again, by Fermat's little theorem. And what about A over P? A over P is also 1. A to power P minus, so see, we are saying that case 1, basically. Let's say case 1. If A is a quadratic residue, by definition of quadratic residue, A can be written as B squared. So A to power P minus 1 over 2, we simplified with size equal to 1. What about A over P? A over P will also 1. Why? Because again, by definition of Legendre symbol, so we said that this symbol is called Legendre symbol. By definition of Legendre symbol, A over P is equal to 1 if A is a quadratic residue. And in case 1, I'm assuming A is a quadratic residue. So in this case, and A over P equals 1, since A is assumed to be a quadratic residue in this case. So we can say that A over P equals A to power P minus 1 over 2 equals 1 in ZP. Now, case 2, if A is not a quadratic residue, then my claim is that A to power P minus 1 over 2 minus 1 will not be equal to 0 in ZP. Why? In case 1, we saw that if A is a quadratic residue, then A to power P minus 1 over 2 minus 1 equals 0, because we showed that A to power P minus 1 over 2 equals 1, which is same as saying that A to power P minus 1 over 2 minus 1 equals 0. Now we are saying that if A is not a quadratic residue, then this expression will not be equal to 0. Of course, this is not obvious, right? Because these two statements are not equivalent. The fact that if A is a quadratic residue implies that this expression here equals 0 is not same as saying that, or does not imply automatically that if A is not a quadratic residue, then this expression is not equal to 0. Because potentially it's possible
that this expression equals 0 for every quadratic residue, and maybe also equals 0 for some quadratic non-residues as well. The fact that this expression equals 0 for quadratic residues, it doesn't mean that it's not equal to 0 for non-quadratic residues. Maybe, as I said, potentially, for some quadratic residues, this could be still 0, potential. But my claim is that that's not the case, and for every quadratic non-residue, this expression will be not equal to 0. Why do you think that this is true? The reason is coming from a theorem that we saw last time, Lagrange theorem for polynomials, for zeros of polynomials in ZP, which was saying that every polynomial of degree n has at most n roots in ZP. Well, of course, if you consider in Z or in R, every polynomial in R or Z of degree n has at most n roots. But Lagrange theorem says that the same rule holds even if our universe is ZP. So every polynomial of degree n has at most n roots in ZP. So proof of claim. We saw last time that every polynomial of degree n has at most n roots in ZP. I think we called it the Lagrange theorem, right? Now, let's say f of x equals x to power p minus 1 over 2 minus 1 has p minus 1 over 2 roots roots which are quadratic residues, which is what we showed in case 1. In case 1, we showed that every number which is a quadratic residue is a root of this function. That's what we did in case 1. But how many quadratic residues do we have in total? The theorem before this theorem, we showed that we have exactly p minus 1 over 2 quadratic residues. We have p minus 1 over 2 quadratic residues. So if every quadratic residue is a root of this function f, and we have p minus 1 over 2 quadratic residues in total, so that means we have no other possibility left, because this function has p at most p minus 1 over 2 roots, and I already found p minus 1 over 2 roots for it. So no other possibilities left to be a root of this function other than these p minus 1 over 2 quadratic residues. So that means no other number can be a quadratic, can be a root of f of x. So that means f of x not equal to, or f of a not equal to 0 if a is a quadratic non-residue. This function, so I repeat one more time the reasoning. This function is a polynomial of degree p minus 1 over 2. And therefore it has at most p minus 1 over 2 roots. But I already found p minus 1 over 2 roots for this. Which p minus 1 over 2 roots? All the numbers which are quadratic residues in ZP. So if I already found p minus 1 over 2 roots for this function, and it has at most p minus 1 over 2 roots, that means no other number other than the numbers that I found can be a root for this function. So that means f of a not equal to 0 if a is a quadratic non-residue. So what does that mean? So we show that if a, so we are in case 2, that a is not a quadratic residue. So that means a to power p minus 1 over 2 minus 1 not equal to 0 if a is quadratic non-residue. And if a number not equal to 0 in ZP, what does that mean? That means that number is not divisible by p. Now this number is not divisible by p, but look at this one. We know that either this number or this number must be divisible by p. So this, if a is quadratic non-residue, this number will not be divisible by p. So that means this number must be divisible by p. So that means, so let me say by star above, p divides a to power p minus 1 over 2 plus 1. That means a to power p minus 1 over 2 plus 1 equals 0 in ZP. And that means a to power p minus 1 over 2 equals minus 1 in ZP. Again, remember, if a number is divisible by p, that number is 0 in ZP. So in case 2, so in this case, what can we say? A over p, Legendre symbol, equals minus 1. Because remember, we are in case 2, where we are assuming that a is a quadratic non-residue. So if a is a quadratic non-residue, a over p equals minus 1, which, as we saw, is same as a to power p minus 1 over 2. That means in any case, a over p equals a to power p minus 1 over 2. We saw that if a is a quadratic residue, both of these numbers are 1, and if a is quadratic non-residue, both of these numbers are minus 1. Okay, now the next theorem, again, if p is a prime number, and 0 not equal to a in ZP, and also b, let's say we have two numbers, 0 not equal to a in ZP, and 0 not equal to b also in ZP, then AB over P is equal to A over P times B over P. So of course, you remember that this is just a notation and it's not an actual fraction. If it was actual fraction, A over P times B over P would be AB over P squared, but this has nothing to do with the fraction. It's just a notation, which is quadratic is equal to 1 if this number here is quadratic residue, and if it's minus 1 if this number here is quadratic non-residue. So let's see how, first let's make an example of this and then we can prove it. So again, let's say p equals 5, a equals, let's say 2, b equals 3. So we saw above, in the example that we did previously, we saw that 2 and 3 are quadratic non-residues mod 5. So what does that mean? That means 2/5 and 3/5 are -1, because 2 and 3 are quadratic non-residues. And so 2, so that means 2/5 times 3/5 will be -1 times -1, which is 1. Also, what about, so my A here, see, my A is 2, B is 3. A over P times B over P will be -1 times -1, which is 1. What about AB over P? 2 times 3/5. So that's 6/5. But what is 6? 6 is same as 1, right? In Z5, 6 is same as 1. So this is same as 1/5. And 1/5 is 1. Why? 1/5 is 1 because 1 is a quadratic residue. 1 is, of course, 1 squared, and any number squared is quadratic residue. So 1 is a quadratic residue. Please look at the example that we did above. We showed that in Z5, 1 and 4 are quadratic residues, and 2 and 3 are quadratic non-residues. So 1/5 and 4/5 are 1, and 2/5 and 3/5 are -1. So here 1/5 is 1, which is same as AB over P, and A over P times B over P is also 1. So in just an example of the theorem, which said that AB over P is same as A over P times B over P. So we can say 2 times 3/5 is same as 2/5 times 3/5. But of course, again, this is not a proof because the proof has to be in general, but this is just an example of the theorem that we want to prove. Okay, now let's see how we can prove the theorem. So proof of theorem. So AB, so let me say by Euler criterion, AB over P is same as AB to power P -1/2, right? Remember, Euler criterion was saying that A over P is always same as A to power P -1/2. Now my A here is AB. So AB to power P -1/2, and this is same as A to power P -1/2 times B to power P -1/2. So here we used Euler criterion. But well, this one from here to here is just the properties of powers, right? Like xy to power t is x to power t times y to power t. So this part is obvious. And then I can apply Euler criterion one more time. And this is same as A over P times B over P. Because again, Euler criterion was saying that A to power P -1/2 is same as A over P. B to power P -1/2 is same as B over P. We also emphasize here where all equalities in above are in ZP. All the equalities are in ZP. Okay, so these are all, parts of exercises, basically. So these, for example, quadratic residues, there are still parts of exercises in 4.4. But again, because I saw that, these are important concepts and sometimes a little bit tricky. So it could be hard for you if you want to do it just as an exercise. So That's why I decided to cover it in the main lecture. But still, please go over the exercises. There are some, so some of them I have done them as theorems, so the proofs are already done. But please still go over the exercises because there are some still new properties which I didn't cover, and you can do it as exercise. And yeah, so this is basically, this was an introduction for number theory. And again, if you want to learn more about number theory, please take, let's say, probably third year course in math in number theory. And usually the name of the course is Introduction to Number Theory or Elementary Number Theory. Yeah, so we'll continue with the next topic, which is chapter 5, induction and recursion.